Sir, my name is Nandu Thanneeru. Today I'm going to explain about the topic evaluating structural engineering finite element analysis data using multi-wave analysis. Introduction. Multi-wave analysis, also known as tensor decomposition or multidimensional scaling, is a power technique for analyzing complex data sets that have multiple modes and dimensions. It can be used to extract underlying patterns and relationships between variables, even when the data is noisy or incomplete. Structural analysis in finite element analysis, structural static analysis. This type of FEA analysis a scaled model based on proportions. The test maintains that any structure that is sound on a small scale will be able to handle the same interactions with the full scale structure and produce the same results. Types of FEA. Various types of analysis that are possible using FEA: structural, vibration, fatigue, heat, flow, etc. are common types of analysis that can be run. Nonlinear studies are more complicated and expensive to perform. If you are looking for analysis of deforming structures, complicated contact conditions, creep, etc., then you may need to take this route. Applications of finite method in structural analysis. Applications of finite element method in structural analysis. Finite element analysis (FEA) is an extremely useful tool in the field of civil engineering for numerically approximating physical structures that are too complex for regular analytical solutions. Consider a concrete beam with support at both ends facing a concentrated load on its center span. So finite elements analysis are there. Elements in FEA are generally grouped into 1D element, 2D element, and 3D element. 5 types of analysis at different stages of business analytics. A huge amount of data is proceeded, and depending on the requirement of the type of analysis, there are 5 types of analytics: descriptive, diagnostic, predictive, perspective, and cognitive analytics. Finite element analysis. Applications of FEA. We use it to calculate the stresses in highly loaded components in the aerospace, nuclear, defense, medical, chemical, and offshore industries to identify the risks of failure. Extended FEA methods can then be used to explicitly model the growth of cracks to predict the time to failure. By coupling with acoustic or flow solvers, we can calculate the stresses caused by high frequency vibrations in chemical process system and hence their fatigue leads. We use the same fundamental method to calculate the surface electropotential of subsea equipment to optimize the design of passive or active cathodic protection system. Text of structural engineering finite element analysis data. Multi-way analysis can be used to identify important modes of vibration that affect the behavior of the structure under different loading conditions. For example, it can be used to identify the most important modes of deformation in a bridge or building, or to analyze the behavior of different structural components under different types of loading. One approach to multi-way analysis is to use tensor decomposition methods such as Yankov or Parafag, CP or Tucker decomposition. These methods decompose a multi-dimensional array into a set of over-dimensional factors that capture the most important modes of variation in the data. Multi-way analysis can be a valuable tool for evaluating structural engineering finite element analysis data, particularly when dealing with high dimensional and complex data sets. By decomposing the data into lower dimensional components, multi-way analysis can help identify important patterns and structures in the data, which can in turn inform design decisions and improve the performance of the structure. Apply multi-way analysis to structural engineering finite elements analysis data. The data must first be organized into a multi-dimensional array that captures the different modes of variation. For example, the array might have dimensions corresponding to different loading conditions, different structural components, and different time points. Once the data has been organized in this way, tensor decomposition methods can be applied to extract the most important modes of variation. These modes can then be visualized and analyzed to gain insights into the behavior of the structure under different conditions. Once the data has been organized in this way, tensor decomposition methods can be applied to extract the most important methods of variation. These modes can then be visualized and analyzed to gain insights into the behavior of the structure under different conditions. To apply multi-way analysis to structural engineering finite element analysis data, the data must first be organized into a multi-dimensional array that captures the different modes of variation. For example, the array might have dimensions corresponding to different loading conditions, different structural components, and different time points. Once the data has been organized in this way, Tensor decomposition methods can be applied to extract the most important modes of variation. These modes can be visualized and analyzed to gain insights into the behavior of structure. One's approach to multivariate analysis is to use tensor decomposition methods such as CAN-FORM, paraFORM, or Tucker precision. These methods decompose a multidimensional array or tensor into a set of lower dimensional factors that capture the most important modes of variation in the data. Once the data has been organized in this way, tensor decomposition methods can be applied to extract the most important modes of variation. These modes can be visualized and analyzed to gain insights into the behavior of the structure under different conditions. Conclusion. Overall, multi-way analysis can be a powerful tool for analyzing structural engineering, finite element analysis data, allowing engineers to better understand the behavior of structures and design more effective and efficient structures in the future. Thank you, sir.